Well, good day, students. We're doing a combustion reaction today, actually two. If you want to consider, we got three separate places, perhaps even three. The first one is one that you're very familiar with, is combustion of methane. Methane is the gas found in our outlets that we use at school. It's CH4, it's a gas state. Mixes with oxygen in the air. Of course, you know, in the air that we breathe, it's not 100% oxygen, so it's around 21% at our elevation here. Of course, if you want to do a little bit of research on that, you can find out exactly what elevation we are and do your calculations based on that. So that's going to make our products here of carbon dioxide and water, which is, by definition, if you will research that, you'll find that combustion takes a fuel in the presence of oxygen and releases carbon dioxide and water. So it's going to release heat. So I'm going to go ahead and do that. I'm going to light up our burner here. Got gas escaping. All right, we have a yellow flame, which means incomplete combustion of the fuel. So we're going to open up the ports and allow more oxygen into that. This is a flare tip, which I put on there so I could show you how to bend some glass at some later point. And of course, the smaller the particles are, the more, gotta have a little fun with stuff, right? So that's the combustion of methane, very simple. I don't have exactly, it's about 3 psi, which is pounds per square inch per minute. So that's about what that is, and we'll go ahead and turn that off so I don't have an open flame unattended. So the second one is one I'm going to do a little bit with those two containers over here. We have two very controlled volumes. We have the plastic one here, which is 11.3 liters. And we have a glass one here, which is at 19.65 liters. And if you do your calculations on those, you know that if you take those values, multiply it times 0.21, you're going to get 4.13 liters of oxygen in the larger one and 2.37 liters in the smaller container. So what I'm going to do is I'm going to take, this is the methanol, I'm going to take about 10 milliliters. I'll put about 5 in each. All right. So we got approximately the same in both. Fairly close. I'm going to close this up. Now, I'm going to let it mix for a few minutes because we want to create a fuel mixture. Kind of let that kind of surface around on the inside of that. And then do the same thing with this one. And then, to show the reaction, like I said, we had the smaller container. I think I calculated it to be 2.37 liters. You can go ahead and check that on your own. And the large is I calculated it to be 4.13 liters. Now, again, the size of those is greater. The larger one we said was, the smaller one was 11.3 overall, and that's total liters, and the other one was 19.65 liters. Okay, so again, that just to show you a comparison between the nitrogen compound, nitrogen molecule in there as opposed to the oxygen. All right, so I think it's given enough time to mix. So I'm going to take a little bit of heat source here. I'm going to light this up again. Use this as my source. Turn that down just a little bit. And okay, I'm going to take, first of all, the smaller one of the two. I'm going to use this flame, and I'm just going to drop it in it because I'm predicting it's going to shoot flames out the top. That did a little bit. Reaction, we see feel some heat here. See some condensation on the inside, which is evidence of the water present, obviously warm, Okay, so next we're going to do the larger container. All right. Have a little bit of flame on the bottom, and you can see condensation on the side, on the top and the sides as well. Now, when this reacts, we also have a lot of allergies. Anyway, you see carbon dioxide is also present. And so I'm going to try to see if there's any excess alcohol in that. So I'm going to blow in that and see if I can purge out, and we'll try it again, see if there's any residual fuel still in there. I still see some liquid in there. I think some of that's water, but it may have some alcohol in it. Now, even blowing some carbon dioxide from my lungs in there, it's going to have some oxygen in it. So what we're trying to do is purge out some of the residual carbon dioxide. All right, so let's try that again and see if we get any flame at all. That was interesting. So based on that, you would think that there's more fuel in that. And so we have to assume that I added some more oxygen to it. If that works, let's try this one. Let's see if we can get anything going on with it. That works well, when you think about the CPR technique with adding extra oxygen breathing for an individual who's having trouble. Let's see what we got. Nothing. Larger container. Maybe I just didn't get as much in there. Well, it has worked before. Obviously not this time. Let's try a little bit more with our reaction here with the stoichiometry, and then we'll be done for our lesson today. I'm going to erase this. We're going to use the, I guess we use the smaller value. You can set it up the same way. we use a 2.37. All right, we're going to use what we did earlier. We're going to calculate using this equivalency and our balanced equation, number 2. And we're going to see how much carbon dioxide could be produced, because obviously carbon dioxide does not support combustion. Apparently I didn't get enough of it out of there, so I'm going to put that as a question mark and going to have it. But there's something we're missing though. We haven't balanced our equation yet. So let's take a moment and do that. So we have one carbon, that looks good. We have 4 hydrogens and 2 hydrogens. That won't work. Let me go ahead and get a light on, make it a little easier to see. All right, so if we're going to do that, I'm thinking we're going to need to have this oxygen where it's a factor of 2. So I'm going to put a 2 there. When I do that, then I have to have a 2 over here for that carbon there. So we have 2 carbon, 2 carbon. But when we did that, we also have 4 hydrogens times 2, that makes 8. So to make that work, we need to have a 4 here, and that will make 4 hydrogens on both sides of the reaction. But when we do that, we have 4 times 1 oxygen, and we have, which is 4, and 2 times 2 oxygen, which also is 4. 4 plus 4 is 8 oxygens to account for. So we have 8 oxygens over there, and we have 2 here. So 2 from 8 is 6. So 2 times what equals 6? 3. So to double check, going from left to right, just like in reading a sentence, to make sure you balance correctly, you do 2 times 1 is 2, 2 times 1 is 2, 2 times 4 is 8, 4 times 2 is 8. Now we're doing the oxygen. 2 times 1 is 2, plus 3 times 2, which is 6, and 2 is 8. 2 times 2 is 4 oxygens, plus 4 oxygens is 8. So we're balanced on both sides. So now we can incorporate our stoichiometry to solve for, say, liters of carbon dioxide. So we set up our equation. I think it's easier to see the black, so I'll use it. So we've got our equivalency, which is 22.4 liters of oxygen at STP is equal to 1 mole of oxygen, which is a gas. And then, of course, go to the next step, our balanced equation, which in this case, oxygen is 3. So to kind of stick with some of you sometimes struggle to see where we get that 3. That's the 3 from the coefficient here. 3 moles of oxygen. And we're looking for carbon dioxide. So we're going to put 2 moles of carbon dioxide. Now, I always like to say that's equal to 1 only in the context of a balanced equation, because this side does equal this side with those coefficients, which we have here and here respectively. And they're put that way so their units cancel as we go. Okay, then we're going to the next step. We're going to be comparing to liters, so we're going to be doing 1 mole of CO2, and again, 22.4 liters of CO2. Now, the interesting thing about this is, as you can see, liters cancels liters, moles cancels moles of oxygen, moles of carbon dioxide cancels moles of carbon dioxide, and 22.4 cancels 22.4. We're simplifying the question. So quite simple math, 2.37 times 2, the only thing left is liters of CO2 over 3. I think you can do the math on that. So hope you enjoyed our little demonstration today, and you have a good day.